you can see here that there are precipitates in several of these test tubes and in the beaker, because these compounds are what we consider to be insoluble. However, even though we say that they, quote, don't dissolve, really small amounts of them do. And we're going to take a look at the equilibrium of these types of substances. In order to do that, you're going to need this green references book, starting on page 15. So that'll be useful as we work through things. So we're looking in chapter 16 with slightly soluble salts. Molar solubility, a new definition, is the concentration of a substance dissolved in water in moles per liter. And when we talk about the solubility product, KSP, it's an equilibrium constant for ionic solids dissolving into cations and anions. And these have to be figured out experimentally, but you have a chart of them, page 15 of the references, or in the appendix C2 in the back of the textbook, which you can get online. So we can write the KSP expression for any ionic solid dissolving into its ions. So I will start with calcium carbonate. The formula for calcium carbonate is CaCO3. So the cations and the anions are all that we need in the equilibrium expression. Because we always have a solid as our reactant, we are only going to have the numerator. The denominator will essentially be 1, but we don't write it. So pause for a second and try magnesium phosphate. Check your answer, and then iron 3 hydroxide. Okay, are you back? Hopefully you figured out the formula for magnesium phosphate was Mg subscript 3 parentheses PO4 parentheses 2. So the KSP is the magnesium ion concentration cubed times the phosphate ion concentration squared. And here's the reaction for the dissolution of magnesium phosphate. Pause again and try iron 3 hydroxide. Is this what you got for iron 3 hydroxide? If not, take a look at your ions and your ion charges. You still need to know your ions, and you still need to know the charges on your ions. As I've written up at the top, we've already done these calculations. We just called them an equilibrium constant. So typically, just like we can with other equilibrium problems, if you're given the equilibrium constant, you can find equilibrium concentrations. And if you're given equilibrium concentrations, you can find the equilibrium constant. So we'll try finding the concentrations first. And I will walk you through this problem. You'll be able to try some more. So we start off with the equation. The solid calcium fluoride is dissolved, forming a calcium ion and 2 fluoride ions. We set up the Rice problem, and with all solids, they're not part of the equilibrium constant. So just put a dash there. We start off with 0 for our calcium and our fluoride ion concentrations, because we're talking about just putting the solid in there. The reaction has to go to the right because we have to make more ions, because right now we have no ions. So we have the plus X and the plus 2X because of the 2 on the fluoride. So at equilibrium, we have X amount of calcium ions and 2X amount of fluoride ions. Then we can plug it into our KSP expression, which is calcium ions times fluoride ions squared. So I take my equilibrium constant that I'm given, X and 2X. Make sure the 2 is in the parentheses along with the X when you do 2X parentheses squared. And if I simplify this, it becomes 4X cubed. That's much easier to solve than the quadratics we've been solving. Divide by both sides by 4 and cube root. And so we have X is 0.011 molar. That allows us to figure out the calcium ion concentration. And it allows us to figure out the fluoride ion concentration. But the second question, what is the molar solubility? It turns out when you want to know how many moles of the substance dissolve per liter, that's the definition of molar solubility. Molar solubility is X. So it turns out that in this case, it's 1.1 times 10 to the negative 3 molar. So not very much dissolves. So we consider calcium fluoride to be insoluble or slightly soluble because we can't dissolve very much of it in water. So when we make a solution, it doesn't look dissolved to us. Here's the other type of problem. And in the homework, you'll see that we're doing both types. I'm giving you the solubility, so I want the equilibrium constant. So this number right here is my X. So we'll start a rice problem. First thing you need is you need to know its formula, silver chromate, Ag2CrO4. Then you need to know it breaks up into 2 silver ions and a chromate ion. And then I start filling in my rice table. Pause if you need to reflect and try to figure out why there's a 2X here and an X here. Now, molar solubility of silver chromate is 6.7 times 10 to the negative 5th, so I know X. So here's my equilibrium expression. So it's 2X parentheses squared times X. So I can plug in my numbers. Now, I actually put it backwards, but it doesn't matter, it's multiplication, so you're allowed to do that. Here is my chromate. Here is my silver ion squared. And if you're a math teacher, you really don't like when somebody does that with exponentials, and scientific notation. But it makes it easier because now I was just able to do it in my head, and the calculator is going to figure out what I mean. So I just do it that way. Plug it in the calculator, and that's what you should get. Try plugging these in your calculator to make sure that you're getting the same answer, making sure we do order of operations correctly. In this picture, I'm actually showing you how we formed the silver chromate. We took some sodium chromate and silver nitrate and just added little bits together, making this brick red precipitate. So let's try to decide how much sodium chromate do I need to make the precipitate. Actually, we're going to use a different one. We're going to use strontium chromate. The math is easier. I forgot about that. Okay, so let's take a look at this problem. If I want to know if a precipitate's going to form, I have to compare Q and K for the reaction. I know K because it's right here. I have to calculate the Q. So to find Q, I'm dealing with chromate ions and strontium ions. And my initial strontium is 1 times 10 to the negative third, and my initial chromate is 3 times 10 to the negative second. So because it's a fairly simple equilibrium expression, all I have to do is multiply, and I end up with 3 times 10 to the negative fifth. That's the first step. Second step, we need to compare Q and K. So we found Q. Here is K. And it turns out that Q is less than K. If Q is smaller, then we know that we have too little product, and in this case, the product is the ions, which means we're not going to make a precipitate. We're going to keep dissolving. It is as dissolved as it's going to get, and we could even dissolve more. The reaction shifts to the right because of Q and K, and so we will not see a precipitate. So pause for a minute and do the same thing with the second one. Now that you've had the chance to try a similar equation, the only difference is our value for Q. And in this case, Q is greater than K, so it's going to shift towards the product, towards the reactants, sorry. It's going to shift towards the reactants, and so the solid is going to form. We will see a precipitate. So all you need to do to determine if a precipitate is forming is use the initial concentrations compared to the equilibrium constant. Now this one is a hard problem. So take a minute or two and see if you can figure out part 1 and part 2. And when you're ready to go over them, we'll take a look at the answers. All right, hopefully you've tried these. I decided that calcium fluoride would precipitate first because we could compare the calcium fluoride and the barium fluoride. And the calcium fluoride has a much smaller equilibrium constant. Therefore, it will make a precipitate first. We need less fluoride to make it precipitate. If you've tried the second problem, we'll take a look at it. If not, pause again. Okay, so the second problem, I need my KSP. It's the calcium ion times the fluoride ion. And let's figure out what I need to figure out. I know my KSP, it's written up here. I know my calcium ion is 0.1 molar. The only thing I don't know is my fluoride ion. So I could write a Rice problem for this, but I'm not even going to. 3.5 times 10 to the negative 11th divided by 0.1, and then square root it. That's my fluoride ion concentration. Now pause and try the problem in the next block. All right, hopefully you noticed that it's a continuation of the problem before. We need the minimum volume of sodium fluoride. So I'm going to use, here's what we need and what we have. We have 1.9 times 10 to the negative fifth in 500 milliliters of solution, so those two have to go together. And we have 0.2 molar solution, that will have to go with a new volume. So if I have two molarities and two volumes, M1 V1 equals M2 V2. I plug them in, making sure that I get the top two on one side and the bottom one and the unknown on the other side. And I solve, and I have a tiny little amount. So now you know enough about equilibrium constants when we're dissolving solids that you can try some problems on your own. If you have any questions, let me know, and good luck.